Welcome to This Explainer. We're going to embark on a truly fascinating journey today. We are literally stripping away the sleek exterior of modern electric vehicles to demystify the mechanical magic happening underneath. You know, we've all seen them gliding quietly down the street, feeling almost like they've just dropped in from the future. But what is the actual anatomy of that movement? How do we take static energy and transform it into such thrilling, immediate motion? Well, we're going to break down the architecture of motion itself. Let's get right into it. It brings us to a really fundamental mystery. Think about it. How does a heavy, multi-ton metal box go from 0 to 60 miles per hour in just a matter of seconds, completely bypassing the loud noises and violent internal explosions we've relied on for over a century? Seriously, where does all that silent, massive power actually come from?
Okay, let's dive into this. For decades, our vehicles have basically relied on a symphony of controlled chaos. We're talking pistons firing, literal explosions happening thousands of times a minute, and a really complex traditional gearbox trying to manage all that aggressive mechanical energy. It's inherently noisy and, frankly, incredibly complex. But the electric vehicle, it abandons all of that. No pistons, no internal explosions, no traditional gearbox. It operates in near absolute silence. We're essentially trading mechanical complexity for streamlined, incredible elegance. And to really understand how this elegant system works, we need to examine its anatomy, one vital organ at a time. And, well, every great system starts with a source.
Section 1. The giant power bank, the source of the energy. So when we say power bank, you might be picturing that little rectangle you plug your smartphone into when it inevitably dies at 2 p.m. But scale is literally everything here. An electric car battery stores tens of thousands more energy than the device sitting in your pocket right now. We aren't dealing with a few thousand milliamp hours. No way. We're talking about a massive, high-voltage energy reserve that takes up the entire floorboard of the vehicle. Now, what's truly fascinating is how that massive scale is achieved through thousands of tiny, perfectly organized units. Because if you were to open up that giant battery pack, you wouldn't just find one big vat of energy. You'd actually find thousands of individual lithium-ion cells. Each one of these cells stores electricity chemically. They just sit there, holding immense potential, basically waiting for your command. And the absolute second you press your foot on the accelerator, these cells instantly begin converting that chemical storage into electrical energy, releasing it on demand. But here's the catch. All that raw electrical energy rushing out of the battery can't just go directly to the wheels. I mean, it would be total chaos. It needs a smart middleman, a conductor, to direct the symphony.
Which brings us to Section 2, the drivetrain's electronic brain, the power controller.
The power controller is exactly what it sounds like. It's the brain of the whole operation. In a traditional gas car, pressing the pedal literally opens a physical fuel valve to dump more liquid into an engine. But in an EV, when your foot presses down, you're just sending an electronic signal. The controller takes that signal and instantly translates it to figure out exactly how much electrical power needs to be delivered to move the car at the exact speed you want. It builds into this lightning-fast sequence. First, your foot sends the signal. Next, the controller calculates the exact power needed. If it sends too little, the car feels sluggish. If it sends maximum power, well, you're pinned to your seat. Finally, the exact perfect amount of energy is dispatched. And honestly, the most mind-blowing part, this process doesn't just happen once. The controller recalculates this thousands of times every single second to ensure your ride is perfectly smooth. Okay, so the battery has released the energy, the controller has perfectly measured it. Where does it actually go? It goes straight to the beating heart of the vehicle.
Section 3. The heart of motion, the electric motor.
If you've ever looked under the hood of a gas car, you know engines have hundreds of moving parts, right? Belts, valves, camshafts, the whole shebang. The electric motor, by contrast, is an absolute masterclass in minimalism. It has very few moving parts. Instead of explosions, it relies entirely on the invisible, powerful forces of electromagnetism. It converts electrical energy into physical motion simply by using continuous magnetic attraction and repulsion. It's almost like magic, but it's just really good engineering. And it brilliantly illustrates exactly how that invisible force turns into forward momentum. First, the precisely measured electricity from the controller flows right through coils of wire inside the motor. Second, that flow of electricity instantly creates a magnetic field. Third, this new magnetic field interacts with the permanent magnets inside the motor. They continuously attract and repel each other in a rapid, endless chase. Fourth, that incredible magnetic force causes the centerpiece, called the rotor, to spin. That spinning rotor turns the drive shaft turns the wheels, and boom, you're moving. This magnetic process is the absolute secret behind that famous EV acceleration we talked about at the beginning. In a gas car, you've got to wait for the engine RPMs to build up before you feel the real power. But magnets? They don't need to rev up. Because the electric motor uses instant magnetic forces, it produces maximum torque instantly. Zero waiting. That is exactly why electric cars feel incredibly quick and responsive, the literal millisecond you press the pedal from a standstill. Now that we've got the vehicle moving with incredible speed and power, the engineering challenge shifts a bit. How do we make sure we don't waste that precious energy?
Section 4. Maximizing efficiency and range, gears, braking, and cooling.
First, let's talk about gears. Gasoline engines have a critical flaw. They only produce their maximum power within a very narrow RPM range. That's exactly why they require complex transmissions with multiple gears to keep shifting as you speed up. Electric motors are entirely different. They deliver highly useful power across a massive, wide speed range. Because of this, most electric cars only need a single-speed reduction gear. So, by eliminating all those extra gears shifting back and forth, you get less friction, much higher efficiency, and, for sure, significantly less maintenance.
But hey, the efficiency doesn't stop with the gears. When you slow down in a normal car, hitting the brakes basically turns your forward motion into heat, and that energy is just lost forever. But in an EV, watch this. At millisecond 1, you lift your foot off the accelerator. By millisecond 2, the motor actually starts working in reverse. Millisecond 3, it stops consuming power and instantly becomes a generator. The momentum of the spinning wheels actually rotates the motor, and then in millisecond 4, that physical rotation produces new electricity that flows right back into the battery. This ingenious loop is called regenerative braking. You are literally recapturing kinetic energy to extend your driving range and save wear on your brake pads. It's a real game changer.
Of course, even with regenerative braking, eventually you've got to plug in. And how you charge matters. If you use a standard home charger, it's a slower process because the energy has to filter through the car's onboard electronics to convert it properly. But a fast DC charger takes a totally different approach. It actually bypasses those onboard electronics entirely. By injecting direct current straight into the system, it delivers massive power directly to the battery, adding hundreds of kilometers of range in less than 30 minutes. But pushing all that massive energy in and out of the battery creates a final challenge: heat. Batteries are exactly like humans. They absolutely despise extreme temperatures. If they get too hot, their lifespan permanently decreases. If they get too cold, their daily performance drops dramatically. That is exactly why these vehicles are equipped with really sophisticated liquid cooling systems circulating around the modules. These systems constantly work behind the scenes to keep the battery sitting in its perfect, ideal operating temperature, ensuring longevity and maximum power. So the crucial point is that when you put all these systems together, the illusion of overwhelming complexity just fades away. Leading us to Section 5, the elegant simplicity, the final blueprint. This right here is the incredibly straightforward chain reaction that replaces the violent explosions of the past century. Think about it. The massive battery simply stores the chemical energy. The brilliant controller meticulously manages and measures that power. The motor uses invisible magnetic fields to convert that electricity into physical motion, and the wheels turn. It is a straight, clean, logical line of energy from storage to movement. This brings us to a quote from our source material that perfectly captures everything we've explored in this explainer today. The technology may seem futuristic, but the basic principles are surprisingly elegant. Hit the nail on the head, right? By drastically reducing the number of moving parts, engineering has given us a machine that is quieter, requires far less maintenance, and operates with a level of efficiency that combustion simply cannot match. It's not just a different way to drive, it's a fundamentally cleaner way to engineer motion. The systems we looked at today, the rapid chemical batteries, the lightning-fast controllers, the magnetic motors, they're absolutely incredible, yet they represent just the early chapters of this technology. So if this simple, silent elegance is just the beginning, what on earth will the architecture of motion look like in 10 years? Thank you so much for joining me on this explainer. I really hope you never look at a passing car the exact same way again.